Dear students, today we will study and analyze Norton theorem. Let's begin with the definition. Norton theorem is similar to that of Thevenin's theorem. It states that any two terminal in a linear network or circuit can be represented with an equivalent network or circuit which consists of a current source in parallel with a resistor. You may remember that in Thevenin theorem we had a Thevenin's voltage connected in series with a Thevenin's resistor which was connected to a load. However, in Norton theorem we have a Norton current source connected in parallel with a Norton resistor. The equivalent circuit is known as Norton equivalent circuit. A linear circuit may contain independent sources, dependent sources and resistors. If a circuit has multiple independent sources, dependent sources and resistors, then the response in an element can be easily found through replacement of the entire network to the left of that element with the Norton's equivalent circuit. In Thevenin's theorem, we found the response of the RL or load resistance with the help of Thevenin's equivalent circuit. Similarly, in Norton theorem, we will find the response of the respective element which is connected to the right side of the circuit with the help of Norton's equivalent circuit. The response in an element can be the voltage across the element, current flowing through the element, or power dissipated across that element. This concept is illustrated in the following figure. Similar to that of Thevenin theorem, Norton theorem can also be represented through this diagram. We have a two-terminal linear circuit here, points EB here, which are represented for the distinguishing of load. This circuit can also be represented as a Norton current connected in parallel with the Norton resistance, which is then connected to the load. Now, the Norton equivalent circuit resembles a practical current source. Therefore, it is having a current source in parallel with the resistor. You can see we have a Norton current source with that of a Norton resistance. The current source is present in the Norton equivalent circuit and is known as Norton equivalent current or simply Norton's current and is represented by IN. Similarly, the resistor present in the Norton equivalent circuit is known as Norton equivalent resistor or simply Norton's resistor and is represented by Rn. There are different methods to follow for solving the Norton theorem. First method is when you have sources of independent type in the circuit. Step 1 is you have to consider the circuit through opening the terminals with respect to which the Norton equivalent circuit is to be found. Step 2 to go with is finding the Norton's current IN by shorting the two open terminals of the circuit. Step 3 is finding the Norton resistance across the open terminals of the circuit as considered in step 1 through elimination of independent sources present in the circuit. Now, the Norton's resistance Rn will be exactly same as that of Thevenin's resistance. Step 4 to follow is drawing the Norton equivalent circuit by connecting a Norton current in parallel with the Norton resistance. After that, you can find the response in an element that lies to the right side of the Norton equivalent, which is usually load resistance. Method 2 to follow is when you have sources of both independent and dependent type in the circuit. Step 1 is consider the circuit by opening the terminals with respect to which the Norton's equivalent circuit is to be found. Step 1 is exactly the same as that of method 1. Step 2 is you have to find the open circuit voltage across the open terminal of the circuit. Step 3 is finding the Norton current IN through shorting the two open terminals of the circuit. Step 4 is then finding the Norton resistance Rn through using the formula Rn is equal to V open circuit divided by Norton current. Step 5 is drawing the Norton equivalent circuit by connecting Norton current in parallel with the Norton resistance. After that, you can find the response in an element that lies to the right side of the Norton equivalent circuit. As far as method 3 is considered, it is an alternate method for finding the Norton's equivalent circuit. The step 1 is finding a Thevenin's equivalent circuit between the desired terminals. We know that it consists of a Thevenin's voltage source VTH and Thevenin's resistor RTH. Step 2 is getting the Norton equivalent circuit through application of source transformation technique to the Thevenin's equivalent circuit. Therefore, the Norton current is IN is equal to V Thevenin divided by R Thevenin. The Norton resistance is Rn is equal to R Thevenin. It has been discussed that the Thevenin resistance is exactly the same as Norton resistance and vice versa. This concept is illustrated in the following figure. Here we have Thevenin's voltage source connected in series with a Thevenin resistance, and here are our respective points A and B. Now this circuit can be transformed into Norton's circuit if we transform this circuit into this one. For that we need to get rid of our voltage source and get a current source and place the Thevenin resistance as Norton resistance but in parallel to the current source. Only after that we can find the response of an element by placing the Norton equivalent circuit to the left hand side of the element. Here we will place our element R load resistance and we can find its response. Let's proceed to our example. Consider the following circuit. This is exactly the same circuit that we considered for Thevenin's theorem. We have 20 volts of source, 3 resistors connected in a form of load, and we have a 4 ampere current source and load resistance of 20 ohm. We will take method 3 for solving this circuit. So for that, step 1 is going to be transforming this circuit into a simple version, that is Thevenin resistance and Thevenin voltage. Now do you remember the steps for getting Thevenin voltage and Thevenin's resistor? If not, then let's revise it. First of all, we need to take off our 20 ohm RL. After that, we have to apply nodal analysis at our node V1, and we are going to get V1 minus 20 divided by 5 plus V1 divided by 10 minus 4 is equal to 0. Taking 10 as an LCM, we will have 2V1 minus 40 because we have 2 for this plus V1 and we have to multiply 4 by 10. So we get minus 40. Now we take 10 to the right hand side, this will be equal to 0. So we have 3V1 minus 80 is equal to 0. V1 will become V1 is equal to 80 by 3. So we get V1 as 26.66 volt. Now we need to find voltage across 10 ohm resistance. So for that we have current of minus 4 ampere and resistance of 10 ohm. So we get its voltage as minus 40 volts. Now we have to apply KVL at mesh 2. So we get V1 minus V10 ohm minus V Thevenin is equal to 0. we get 26.66 minus 40. So our VThevenin is 66.66 volt. Now we will go for finding the RThevenin. We will short circuit the voltage source and open circuit the current source, and we will find our R equivalent, which will be 5 multiplied by 10 plus divided by 5 plus 10 plus 10. So we get our R Thevenin is equal to 13.33 ohms. Therefore, we have Thevenin voltage is equal to 66.6 volt and Thevenin resistance as 13.3 ohm. Now, the step 2 will be application of source transformation technique to above Thevenin's equivalent circuit. So we will substitute the values of VThevenin and RThevenin in the following formula for our Norton current. IN will be equal to VThevenin divided by RThevenin. So we have IN is equal to 66.66 divided by 13.3 ohms. So we have Norton current equal to 5 ampere. We have Norton current equal to 5 ampere. We know that the Norton resistance is the same as that of Thevenin resistance. So we have our N is equal to 40 divided by 3 or 13.33 ohms. The Norton equivalent circuit corresponding to the above Thevenin equivalent circuit is shown in the following figure. Now here we have 5 ampere of current source connected to a 13.3 ohms Norton equivalent resistance connected in parallel to the current source. Now we can place the Norton equivalent circuit to the left of the terminals A and B of the given circuit, and through the current divider rule we can have current at 20 ohms load. So 20 ohm load current will be 5 multiplied by 13.33 divided by 33.33. This is our equivalent for this and load. So we get current equal to 2 ampere. Now we will move forward for our simulation. However, you have to remember each and every step that was performed during calculations as we are going to verify our Norton theorem. So we will go to falstad.com/circuit for simulation of our circuit. Here we are in our falstad. We will clear the circuit. Now we will start building up our circuit. We had 3 resistors in our circuit and the 4th resistor was of load. So we will place resistors first. This is our first resistor, second, third, and it's our load. Our load was of 20 ohms. Third resistor was of 10 ohm. Second was also of 10 ohms, while first resistor was of 5 ohms. We will interconnect the circuit with the help of wires. First, I need to add my current source and change its value to 4 ampere. Now our circuit is almost complete. We need to add our ground and voltage source. So we will add ground here, and now we will put our voltage source and change it to 20 volts. Now our circuit is complete. The first thing we need to do is remove our load. So we will click on select and drag and remove the load. Now our next step is finding voltage at V1 at this point. What we do is we place 3 voltage meters and check the voltages at respective resistors so that we can simplify our simulation. So we'll go to draw, output and labels and place voltmeters here. Now we can connect the voltmeter through wires. Here we are getting negative voltage, so we will swap its terminal. You can see that we are getting voltages in exact the same manner that we got during our calculations. We have 26.6 volts here, minus 40 volts here at 10 ohm resistance. Now we will calculate our VThevenin. For that we need to put our voltmeter right here. So we will go to draw, output and labels and place our voltmeter at this point. We are getting 66.667 volts here, which is exactly the same that we got during our calculation. Now the very next step is to calculate the Theorem, which is also our R Norton. So for that we will short circuit our voltage source and open circuit our current source. So we will delete it and delete it as well. We will also delete all voltage meters and wirings for making our circuit as simple as possible, so that we can calculate our Norton resistance or Thevenin resistance quickly. We will connect this through wires and go to draw and place our ohm meter right here. So we get 13 ohms here, which is our Thevenin or R Norton. Now we will clear the entire circuit and make our new circuit for Norton equivalent circuit. So we will draw resistor. First we need to draw our Thevenin equivalent resistance. So for that we had our 20 ohms load resistance and 13 ohms of Thevenin resistance, and we had voltage source of 66.66 volt. We will connect the circuit. Our circuit is complete except that we have to add ground. Now our circuit is complete. Now we need to convert this Thevenin equivalent circuit into Norton equivalent circuit. For that this Thevenin equivalent will be placed in parallel to a current source here. We calculated our current source to be 5 amperes. So we will delete this voltage source and we will place a current source of 5 amperes here, and we will move this in parallel to our current source. So we will select and drag this resistor in parallel. Here it is not connected, so we will delete this wire and click on wire again. Connect both these and complete the circuit. Now we were required to measure our current for load resistance. So we will delete this wire and go to draw, output and labels, and place an emitter right here. So here we have 1.97 ampere, which is exactly equal to or approximately equal to 2 amperes. So our Norton theorem is verified through simulations. As we are done with the simulations, it's time for your home task. You have to verify Norton theorem for the given circuit, do all the necessary calculations and simulate the circuit. This is the circuit. You have 10 volts of source voltage, 2 kilo ohms of first resistor, 2.1 kilo ohm of second resistor, 500 ohm of third resistor, and your RL is 1.9 kilo ohms. You have to find IL. Best of luck. If you have any queries, feel free to ask. See you in the next lecture.